I'm Daichi Mukunoki from Weekend Center for Computational Science. I'll talk about accurate matrix multiplication and binary 128 format accelerated by Ozaki scheme. Binary 128 is the quadruple precision floating point format defined in the IEEE standard. Currently, binary 128 is not available on x86, but the software emulation is available on GCC, ICC, and so on. However, the performance is extremely slow compared to binary 64 in hardware. The need for high-precision arithmetic like binary 128 is still limited, but it is certainly needed in some applications, and will be needed to suppress the accumulation of rounding errors in large-scale computation. Currently, few numerical libraries support binary 128, but MP-LayPack provides multi-precision brass and LayPack routines using GCC's binary 128 emulation and several high-precision arithmetic libraries such as LPFR and QD. The double-double arithmetic is a fast alternative for performing quadruple precision arithmetic. It is performed using binary 64 arithmetic, and the format is incompatible with binary 128. The QD library is a known implementation of the DD arithmetic. There are several other implementations and performance studies. According to these studies, the DD arithmetic can be performed with about 20 times the overhead of binary 64, but if it is sufficiently optimized. But the performance optimization on CPU is not easy, and hand symbolization is needed. In this study, we propose a fast and accurate implementation of matrix multiplication on binary 128 matrices on x86. It outperforms GEM implementations using binary 128 emulation and DD arithmetic in MP-LayPack. This study is an extension of our previous work, DGEM using Tensor Core GEM, to binary 128 GEM using DGEM. They are based on the Ozaki scheme, which is an accurate matrix multiplication algorithm to compute high-precision GEM using low-precision GEM. In this study, we propose some binary 128 specific optimizations and discuss further extensions of this scheme. Now, we briefly explain the Ozaki scheme used in our implementation. This scheme has already been proposed in our previous studies. Ozaki scheme is an accurate computation method applicable to inner product-based operations. And here, we explain the case of inner product. First, the input vectors are split into several split vectors. This is an element-wise splitting from higher bits to lower bits. Here, the exponent and significand are separated. This splitting is performed so that the inner products of split vectors for x and y can be computed without rounding errors in binary 64. Please see the paper for details. This splitting is based on the error bound of inner product, and the number of split vectors depends on the absolute range of the elements and dimension of the input vectors. Using the split vectors, the accurate inner product is computed as in the equation on the right. Here, the all-to-all product of the split vectors for x and y is computed. Those inner products can be computed using binary 64 without rounding errors. In other words, they can be computed using the d-dot routine in brass. And finally, we compute the summation of them. If you want to obtain binary 128 level accuracy, this summation can be computed with binary 128. But if the summation is computed with infinite precision, you can get the infinite precision result because the inner product computations are error-free. Applying this scheme to matrix multiplication, the overall schematic can be illustrated as shown in the figure. You can use dgem for the product of split matrices, and dgem will dominate the execution time. The execution time increases with the square of the number of split matrices. And let me repeat, the number of split matrices is input dependent. On matrix multiplication, the execution time becomes dgem dominant. But binary 128 operations are needed for splitting and summation parts, and they can somewhat impact the performance due to very slow binary 128 enumeration. In this study, we propose two ideas to reduce the use of binary 128 operation: split 3 and sum 3. But I'll skip the details for the sake of time. These methods can be used only when the input matrices are in the exponent range of binary 64. Also, we apply two more optimizations. For preventing accuracy loss, we optimize the summation order, and for reducing memory consumption, we apply a blocking technique. We implemented the proposed method in C++ on x86. Splitting and summation parts are parallelized using OpenMP. For dgem, we used Intel MKL's dgem routine. Basically, the implementation is straightforward. Since the performance of the proposed method is dgem dependent, we can easily achieve a good performance by using a highly optimized dgem. This is a great advantage of the proposed method. So let me move on to the performance evaluation. We used Skylake CPUs with 24 cores in total. Other details are as listed here. For comparison, we also evaluate the performance of binary 128 gem and double gem in MP-LAPACK. They are implemented with the naive matrix multiplication algorithm with triple loops with OpenMP, but not SIMD optimized. Binary 128 gem uses GCC's emulation, and DDGem uses QD library's DD operation. We evaluated the performance of matrices with different absolute value ranges. This is because the performance of our implementation depends on the input range. The range is varied by R, like this. This figure shows the maximum relative error of each implementation versus MPFR with 2048-bit. Our implementation achieves higher accuracy than others because most computations are performed with error-free. Unlike the other two, the error does not increase as the dimension increases. Next, we show the throughput in flops. Here, flops means the number of quadruple precision operations per second. The performance of our implementation is shown with solid lines with different colors corresponding to different input ranges. The performance is input dependent, but our implementation can outperform MP-LAPACK's implementations. We note that in this evaluation environment, MKL's dgem can achieve approximately 1.6 teraflops, So our implementation has approximately 40 times overhead at best. Here, the top figure shows the number of split matrices. It increases as the input range and the dimension increase. And the bottom figure shows the execution time breakdown. The execution time is DGEM dominant. This means that the performance is determined by the DGEM throughput and the number of DGEMs computed, which also depends on the number of split matrices. This figure shows the performance when split 3 and sum 3 are not used. The dotted line shows the performance without split 3 and sum 3 on R1. In this case, the cost of splitting and summation increases, and the performance decreases to about 80%. In our paper, we discuss several extensions and applications of the proposed implementation, including GPU acceleration, SGEM-based implementation, performance on reduced precision inputs, performance of matrix vector multiplication, and a distributed parallel implementation. Due to the time constraint, we cannot introduce them in this presentation, but we show the performance demonstrations in the paper, except for the last one. This is the summary. We proposed a fast and accurate matrix multiplication on binary 128 matrices using Ozaki scheme. This is a high performance, low development cost, and accurate, but the performance is input dependent. Thank you for your attention.